Today I want to talk about constructible sheaves and exit paths. So let me first sort of remind ourselves about what we did during the first week. So in the first week, what Clark told us was that if T is sufficiently nice topological space, then there's an equivalence. Well, on the one hand, we have locally constant sheaves on T with values in the infinity category of spaces. Oh yeah, so maybe let me say, I'm going to try to, whenever something is a topological space, I'll try to write it with like T or something like this rather than X. And on the other hand, functors out of what I'll call pi infinity of T, that's the underlying homotopy type. So maybe let me write this as mon. This is the non-Fermi equivalence, and this is the underlying homotopy type. And so, right, this is locally constant sheaves. This is just a full subcategory of sheaves on T. And maybe let me say a little bit more about this equivalence. So, I drew it in this way, and when it was the set version, so when spaces was replaced by sets, and then this guy pi infinity T could just be replaced by the fundamental groupoid. You know, Clark explained how you write the equivalence down this way. But partially because of what I want to say later, let me just say a few words about how you can write down an equivalence between these two things. But it'll actually go in the other way. So the easiest way to see this is by this straightening unstraightening equivalence. I'll just write straightening unstraightening. This functor category, so this is an object of the infinity category of spaces, is equivalent to spaces sliced over this underlying homotopy type. And then let me write down the functor in this direction, so that this will be the equivalence that I'll write down. And what it does is you take your space over your given space, and what you do is, well, I need to create a sheaf out of this. So, I mean, I'll write down a pre-sheaf and then I'll claim that it's a sheaf and also locally constant. So the pre-sheaf, it's going to send some U, that's an open subset of the topological space T, to, well, I'll take maps over this homotopy type into Y from the underlying homotopy type of U. So, okay, clearly this is a pre-sheaf. It's actually a sheaf by sort of the infinity version of the Van Kampen theorem. And then maybe it's not so hard to see that it's locally constant either. Because like if you had, you know, two very small opens that were, say, contractible, like, you know, if you're in this sufficiently nice setting, then this is going to induce an equivalence on those. So Yeah, so this description, if you care to read about it, this description is from higher algebra, A.4.19. And I'm saying this now because the point of this talk is going to be to replace locally constant sheaves with something called constructible sheaves, and we'll have to replace this guy too. And then I actually, in order to really state the theorem, it's going to be a bit more complicated. So one of the things that Clark explained in the first talk was that this pi infinity of t, there was a different way of thinking about it as the shape of this infinity topos of sheaves on the topological space T. But in this exit path situation, things will be a bit different. So and I'll kind of need this description.
Hey, Peter, maybe I'll just interject here with less of a question and more of a comment, which is that if you are the kind of homotopy theorist who was raised on stuff like the May-Sigurdsson parametrized homotopy theory stuff, then that's exactly what this homotopy theory is. The homotopy theory of spaces over pi infinity t is really spaces parametrized over pi infinity t. Yeah.
That's a very good point. Yeah, so this is sort of May-Sigurdsson perspective. And I mean, somehow, one of the nice things about the sort of the infinity categorical perspective is in the May-Sigurdsson stuff, you always have to do these X spaces thing, like spaces over and under this thing. And I don't know, the model structures get quite complicated. But at least for me, conceptually, this was a lot easier to think about. I don't know if that's true for everyone, but.
Could I ask a naive question? So implicitly then, you're either assuming that Y is, that's a confibration, Y over the, or you're replacing it by a confibration, a fibrant resolution, I guess.
Yeah. So, I mean.
This is very naive.
Yeah, essentially, So, I mean, I'm working in the infinity category of spaces, so everything is equivalent to, a confibration.
But if I'm back in the model category world, is this pi infinity of U a cofibrant over pi infinity of t, or would I have to, again, choose an appropriate cofibrant resolution?
That's a good question. I'm not sure I know this.
It is cofibrant. I mean, if you care, because it's the total singular complex, and every simplicial set is cofibrant.
Even in the the relative situation.
Yeah, in the over category of the cofibrants.
Yeah, it's cofibrant. That's a good point.
Okay, U is a subset of T, so that's a cofibration down to pi infinity.
It is. Okay, great. That was my question. Okay, bye.
Yeah. Okay. Yeah. So so today. We're gonna replace locally constant sheaves of spaces on T by a larger subcategory of what are called constructible sheaves. So these guys, well, they'll take into account not only this topological space T, but also a stratification. So, I mean, one of the motivations for enlarging the subcategory is like, say you have some open subset of a topological space and you have a locally constant or just constant sheaf on that open subset and you push it forward, it's not going to be locally constant on the big space usually. Like, you know, if you do extension by 0, well, then it's 0 on the closed complement, but it's not 0 on the open piece, so it's not going to be locally constant on the big guy usually. So this constructible sheaves, one of the things that it will allow you to do is sort of enlarge your categories to allow for push forwards, things like this, but we'll get to this in a minute. So here's the sort of outline of what I want to talk about today. So the first thing I want to talk about is stratified topological spaces. The second thing is constructible sheaves. Then I'll talk about the replacement for this underlying homotopy type, and we'll want an equivalence like this, where this is constructible sheaves and this is something else. So we'll need that replacement. So what are called exit path infinity categories. So these replace this underlying homotopy type in the monodromy story. And well, we're going to be talking about monodromy with this exit path thing, so we're going to call it exodromy, monodromy for exit paths. But before that, I'm going to need to explain what sufficiently nice means in this setting, and it's more complicated than in the sort of classical setting because of some difficulties with how stratifications work. So I'm going to talk about what are called conically stratified spaces. So this will be, essentially this will mean sufficiently nice. Then I'm going to talk about this exodromy theorem. So this is the version of monodromy when you enlarge to constructible sheaves. And then the last thing I want to talk about is what's the homotopy theory of stratified spaces. And talk about some of the difficulties and why a sort of really suitable answer to this has only come into existence in the past couple of years. And so that's sort of the plan. Are there any questions before I say anything else?
Harry has a question, but I'm going to make him save it for just a minute because I think you're going to address something very close to it. So I'll ask it in a minute if that's okay.
Okay, good. So I'll put this to the side. Okay, so yeah, let me talk about stratified topological spaces now. And Clark has so nicely set me up for this already by talking about topologies on posets. So, okay, so here's the basic idea, is that a stratification of a topological space, say T, is a way of breaking T up into disjoint, locally closed subspaces. So remember, locally closed, this means that you're the intersection of an open set with a closed set. So you're closed in an open set or open in a closed set. And so, okay, this is sort of the super vague formulation, but maybe if you've seen stratifications before, it might not be, well, it might not be exactly in the way that I'm going to present. If you've seen David Ayala and John Francis's work, then it will be in the same way. But if you've seen it maybe in algebraic geometry, usually people define a stratification as, you know, some collection of disjoint locally closed subspaces satisfying some conditions. But we're going to sort of put all the structure together. So let's recall from the first talk that if P is a poset, then we have this topology on P, the Alexandrov topology. On P. So on the underlying set is the topology with opens the upwards closed sets. So meaning that if I have an element in my set and some bigger element, then it's also in my set. Here's an observation, is that for every point in my poset, the 1 point set P, well, I can write this as the intersection of the subset of elements bigger than or equal to P with the subset of elements less than or equal to P. So by definition, this subset here is open. And also this subset is closed. So every point is locally closed. Okay, and so to make the idea of stratification precise, here's how I'm going to do it. I'm going to say it's just a space with a map to a poset. So P will be a poset. T. That's a weird T, but that's okay. So P stratification of a topological space, let's call it T, is just a continuous map. Let's call it S for stratification, T down to P. And for P in P, write T sub P for the inverse image of the point P. And this is called the Pth stratum. Of T.
Can you scoot up the paper just slightly?
Oh, yeah. So this is called the Pth stratum of T. And well, notice that by this here, this pth stratum is locally closed. So if you have a map down to a poset in this Alexandrov topology, that breaks up your topological space into a collection of disjoint locally closed subspaces. I mean, satisfying some, some more stuff, but this is the sort of right notion with stratification. And one sort of observation here is, I mean, an observation that we'll sort of make more precise in later talks is, I mean, this makes sense for every topological space, and it works well for the types of topological spaces that arise in algebraic geometry, like underlying spaces of schemes, underlying Zariski topological spaces of schemes. And okay, so that's what I wanted to say about this definition. And so let me give a couple examples of how stratifications work. So here's some examples. So let me write brackets n for the poset that we all love. 0 is less than 1 is less than up to n. So in Clark's talk, he explained how this Alexandrov topological space associated to the poset brackets 1, 0 is less than 1, was this Sierpinski space. So maps down to it classify open subspaces or equivalently closed subspaces. So, so in this setting, if you have a stratification by this bracket n, of some topological space T, there is a generalization of this, this sort of remark in the case that n is 1. A stratification by brackets n of T is exactly the same thing as a filtration by closed subspaces let's call it F0 of T inside bigger guys, inside of F-1 of T, inside of Fn of T, that's going to be equal to T. And yeah, how does this work? Well, if I'm given my stratification, T down to this guy here, well, I send it to the filtration with the ith filtered piece to be the inverse image of 0 through I. And so recall by how this Alexandrov topology is defined, this is a closed subspace of brackets n in the Alexandrov topology. So that's going to be, a collection of increasing closed subspaces. And yeah, if I'm given one of these filtrations, then there's a corresponding stratification to this that, I mean, one can easily check is continuous, and it's characterized by saying that the inverse image of I is equal to F sub I minus F sub I minus 1. And then, okay, when I is 0, by this I just mean empty. And you can check that there is a unique continuous map that satisfies this property. So in the case of brackets 1, you know how this works because maps to brackets 1 classify open or closed subspaces. And so the thing to remark, in case people have seen this before, and if you haven't, it's totally okay. We'll talk about this a bit later. So these are the types of stratifications appearing in the work of Goreski-McPherson. Let's see if I spelled that correctly. I usually misspell that. On intersection homology. Okay, so they have additional conditions that are relevant, and we'll talk a bit more about those later. It's essentially this conical condition, but they only really consider stratifications over this sort of thing. But it's useful to consider stratifications over more general posets. One of the reasons is that, well, if I have a P stratified space and a Q stratified space, and I take their, the product topological space, it's naturally stratified over the product of the posets. So, I mean, that's one reason, but there are lots of other reasons that come from algebraic geometry as well.
So your function S above, right? Just to kind of orient myself, so it can also be described as the minimal I you belong to, right? That's another way to describe it.
Yeah, I think that's right. The minimal, yeah. The minimal I you belong to, yes.
Okay,
yeah,
thanks.
Exactly. Yeah, so maybe let me write that. So yeah, S sub f of little t is the minimal I such that t is an f sub I of t. Thanks, Tomer. Okay, so another, okay, so this is some sort of general example, but there's a key example to think about. Which is that, so let V be a variety over the complex numbers. So there's a natural stratification of V defined by the filtration by singular loci. So inside V, you have the singular locus. And then inside of that may still not be smooth. And you can take the singular locus of the singular locus. And you can keep on doing that. I'm writing that this as a subscript because, saying has and will mean, something else, like saying of something. So by singular loci. So, I mean, it's basically this type of example above. So the picture that you should have in mind for this is, you have this sort of, this is just some schematic shape. You have some shape like this, and well, this big shape, it's not smooth along here and here. This, there's a singularity where this is sort of like, folded and creased. So this green piece, and including the red piece, that's the singular locus. But then that still is not smooth because the green pieces meet in a singular point. But then if you go down to the red piece, that is smooth. And then all of these pieces individually, the red piece by itself, the green piece, and then the orange, they're all smooth by themselves. So so it's a way of breaking your singular variety up into smooth sub-varieties. And so the sort of philosophy I once watched there's some series of interviews with a bunch of mathematicians that the IAS made, and Bob McPherson said something that basically like, my entire career was like, showing people that really you could deal with singularities properly if you just isolated them using stratifications.
I was inspired by that too. That was an amazing thing to say.
Yeah. So yeah, if anyone hasn't seen this, well, especially probably now that, it's kind of hard to do work and you might have some extra time, these interviews at the IAS are really inspiring. There are a lot of different people. Deline is interviewed, for example, McPherson, Yuri
McPherson's
Manin.
actually brought a tear to my eye. It was an incredible interview. It was really gorgeous. It was just so cool.
Yeah, it was really amazing. I would highly recommend watching this. So yeah, the sort of philosophy is that stratifications.
Hey, Peter, real quick, I'll just make a comment that I think that that stratification of singularities is an old result of Whitney's in 1957, a paper called Elementary Structure on real algebraic variety.
Yeah. So we'll talk a bit more about, something. Yeah. So these like Whitney stratifications will come up later as well. Thanks, David. Yeah.
So this is actually something that always confuses me. So is this the thing that is called the Whitney stratification, or is this just an example of a Whitney stratification?
No. Right. This is really early on in all this. And the main result of Whitney's being referenced here is that you can cut out these iterated singular loci through algebraic conditions, which are just, Jacobian matrices of various things.
Got it.
Determinate minors and stuff like that.
Right.
Yeah.
Sure.
Yeah.
And then he also argues that each stratum is a manifold, and then leaves it at that. And later work argues that it's conically stratified.
Yeah. This is work of Tom and Mather, right?
Yeah, exactly.
Right.
Yeah.
Got it.
So
thanks, David.
Yeah. So are there any other questions or comments at the moment?
Throw out my favorite examples, if that's all right, which is moduli spaces of curves, so this goes back to Klein and the 19th century. So as the curve changes, its automorphism group changes. And so you get a nice stratification by finite subgroups of, finite automorphism groups of the curves. Mm-hmm. So it's a slightly finer stratification, but one which, so I especially for genus 2, this was a thesis of a student of Klein in 1890.
Oh, wow.
Pretty cool. Yeah.
Yeah. And of course, like these like Schubert cell decompositions and stuff, give you these sort of structures are pretty ubiquitous.
Wait, who is the student of Klein?
His name was Bolzer, and he became an inaugural professor at the University of Chicago, where he worked on fluid dynamics before rushing back to Germany with the First World War, because it was a bit like now with Chinese in the United States. There was tremendous anti-German prejudice, and Germans were more or less expelled from the country.
Oh God, I see. Right.
Yeah, wow. So, okay. So here's another pretty simple but extremely important example. So there's a natural stratification of, let me write this as bars delta n. So the topological n simplex by the poset brackets n, and let me I have some pictures pre-drawn. Oh yeah, I apologize for anyone who's red-green colorblind, but I had a limited supply of colored pencils in my house. So yeah, well, for delta 0, there's not much to say because bracket 0 is a point, okay? For delta 1, the stratification is the red point goes to 0, and then this complement, which is this green line, everything else besides the point 0 goes to 1. For delta 2, you have the same thing at the bottom, and then you just send the complement of this bottom 1 simplex to 2. So this is, you know, everything above this line. And then you continue in exactly this way. So for the 3 simplex, you do what you had before for the bottom 2 simplex, and then the complement gets sent to the point 3. So, I mean, yeah, if you like equations, you can describe this as sending T0 through Tn in the standard sort of presentation of the topological n simplex goes to the maximum of I in brackets n such that Ti is not equal to 0. I mean, maybe that's not really that helpful, but there's an equation that describes this. We'll see in a second that this thing saying, well, you do the same thing on the bottom and then, you know, the top is just a complement, that's really a special case of a more general type of example.
Mm-hmm. That formula doesn't look right to me. The largest I such that Ti is non-zero.
Yeah.
Yeah. Is this with respect to barycentric coordinates?
Yes, he's thinking of the realization of delta n is sitting inside.
This is where the sum of the coordinates is 1. I'm sorry.
Yeah. Yeah. Okay. I won't write that. Yeah.
I was thinking. Okay, wrong coordinate system. So, thank you.
So yeah, I apologize for not drawing this in that coordinate system, but you know, my drawing skills are only so limited. I felt like if I did some different coordinate system, I'd probably just confuse myself. But okay, so there's a stratification like that, and then here's the observation, is that this actually defines for you a stratification of the geometric realization of every poset. So let P will be a poset. I mean, P is always a poset. So write SDP for the subdivision of P. So that's the poset of non-empty, linearly ordered finite subsets of P ordered by inclusion. So this, non-empty linearly ordered finite subset. Usually Clark and I like to call this a string because this is it's a very long sentence to describe something very simple. So then, well, the poset can actually be recovered as a colimit given by gluing all of these non-empty linearly ordered finite subsets together. So this is just along, the inclusions of these guys. So yeah, let me just remark, of course, this guy is, this guy is just a copy of one of these brackets n's where n is equal to the number of elements of sigma minus 1. So the point is the stratifications.
So Peter, do you think about this as a colimit in the category of posets or the category of topological spaces? Of how in what world should we think about?
So you have to think of it in both, sort of both worlds at once. So yeah, the point is, one second, let me just write one more thing. So
sure.
So this, this geometric realization of delta n, this is the geometric realization of, let me sort of be pedantic and say the nerve of this poset, like I'm thinking about this as a simplicial set. And so these induce a natural stratification from the nerve of P to P, and let me emphasize that this is with this Alexandrov topology. So I'm going to think about this in sort of two ways. So this colimit is in, if first I think about it as being in categories, say, then the nerve actually preserves this particular type of colimit. Because, I mean, what are you doing? You're mapping in the guys that have to factor through one of these things. So the nerve preserves this, and then geometric realization preserves it. On the other hand, in the category of topological spaces, P with the Alexandrov topology is also the colimit of these linearly ordered finite subsets. So these both commute with colimits in P, the poset, as functors to topological spaces. So this gives for you stratification. Does that answer your question, Tomer?
Yeah, thank you.
Yeah, so this is kind of nice. You don't have to, write down some annoying formula. In general, you just get it for free. Okay. Are there any questions at this point?
Am I right that this was just a special feature about brackets ends? Like, it was not because the subdivision category has any, it's not like, that's obviously not filtered. It's not like these are compact objects. It's like this particular colimit. And you have
this
to
particular colimit, and you have to inspect it, right? Because it's a colimit, over these linearly ordered finite things. So the real problem is, the nerve, from categories to simplicial sets that, generally doesn't preserve all colimits. But if you look, when you're mapping brackets n into, P, well, it has to factor through one of these guys anyway. So it actually does pull out here. Mm-hmm. And then everything else is fine with colimits. Yeah, so it's somewhat specific to this situation. But yeah, now let me explain that there's a construction that we'll need, and to get to this conically, stratified stuff, what it means to be sufficiently nice as well. That really says, that this sort of thing that I was saying is like, take the thing that you had before and just like, cone it off, basically. This is actually a special case of a more general construction, but I wanted to draw these pictures because this example. So here's the construction of a new stratified space from an old one. And this is sort of an important thing, and it took me maybe a while to appreciate how important this is. So given P stratified topological space S T to P, construct a space cone of T stratified by this poset. I'll write it like this, P triangle that direction, by which I mean it has a new minimal element minus infinity adjoined. So that's a minimal element as follows. Yeah, so maybe I should say, like, if you have, you know, brackets n, doing this construction gives you brackets n plus 1. So one, so as a set, well, this cone thing is just going to be a new point called minus infinity, adjoin T cross a copy of R greater than 0. So, I mean, basically what I want this to be is just, you know, an open cone on T. I just want to be a bit careful about the details, because it's not just going, the topology on this won't just be the topology on the pushout if your space is not compact Hausdorff.
Right.
So, but what you want to say is that the open neighborhoods in this are going to look like, you know, essentially, if they're away from the cone point, which is this minus infinity, they're going to just be opens in here. And if they contain the cone point, they're going to have to contain a sort of epsilon neighborhood around it. So what's that mean? So U inside of this this set is going to be open if and only if, well, so this first thing, U intersect T cross R greater than or equal to 0 is open. And if U happens to contain this minus infinity, we require that T cross 0 epsilon is in U for some, you know, some epsilon greater than or equal to 0, greater than 0. So yeah, what's that look like? This one, I guess I didn't draw beforehand, sorry. So, you know, it looks like you have your T here. This is sort of, you know, this is the sort of minus infinity part is this sort of point here. Then you have the R greater than 0 part. And then you'll say that some set is open, you know, maybe it has some stuff over here, U. If you want that to be open, you're going to need for it to contain some guy that looks like T cross 0 epsilon. So, so the sort of remark is if T is compact Hausdorff, then this cone on T is really just the push out in topological spaces. Where this 0 gets identified with minus infinity.
So I see why compactness is needed there, but why Hausdorff? Can you give like an example that indicates the problem?
I have the opposite problem. I see why Hausdorff is necessary, but I don't see what compactness is for.
Well, I don't know.
Let's trade.
I mean, yeah, I mean, okay, let's see. Right, because the point is that you want to be able to separate, I mean, you sort of want to be able to separate this cone point from the other points, right? So if you need, maybe compactness is not actually necessary. I'm just sort of hedging
think about T being the real line.
Yeah, compactness is necessary.
Yeah.
I don't know. If
So that epsilon is uniform.
Yeah. Okay.
That's what I'm saying.
I think both of them are necessary, actually.
Oh, interesting.
Because you want to be able to separate this this cone point, right? This condition is telling you that you're able to separate from any other point. You should be able to separate this cone point.
Mm.
So that's like a Hausdorffness, condition.
I suppose it only requires Hausdorffness in a.
Yeah,
Well, but it's T cross. T will need to be Hausdorff. Yeah, no, I see it.
I'm sorry, you're saying that the cone point should be separatable by opens from any other point? Because I think that will already be true just because the real line has that property. So just choose a small neighborhood in the real line that,
Well, I don't know. I'm sort of hedging my bets just because this is what Jacob says. So
Okay.
Maybe it's not completely necessary, but for all the examples we're going to apply this to, basically this is
the usual statement is compact Hausdorff is T4, and then below T4 you have T3.5 and T3, and I bet it's one of those.
Yeah,
Also,
it's probably one of these.
Normal, completely regular, and regular. Yeah.
Well, one way we could test which one it is, we could try and get out the taken off plank and try and perform a construction to it.
Yeah.
What's the plank?
Oh no, it's just I was just being an asshole. It's just the example of a what is it, a T3 space that's not T3.5.
Oh, I thought you were posing a challenge.
No, I'm definitely
While
not.
we're listening to Peter, we all
your
assume
time
the plank
doing
position.
Walk the plank.
You have to, for 2 hours, you must hold a plank. So, the stratification.
I think this is what the kids call planking.
That's definitely what it's about. It's about
right, taking off. As an aside, if anybody can point me to good examples sitting strictly at each of the levels of that hierarchy, I'd be grateful.
I have a whole list of them, Aaron.
Oh, that's great.
I have a bunch of notes where I gave an entire list of every single one that I knew about at the time, but I've actually expanded the list a little bit.
Well, even better.
But
cool,
that one at 3 and 3.5, I think it is really nasty. And
I remember. Yeah.
Did I
have to mention
this at some point?
There's also a book called Counterexamples in Point Set Topology.
Right.
Oh yeah.
It contains all this you could possibly imagine.
That was one of our set textbooks as undergraduates, actually.
Yeah,
so
and
insane.
Harsh.
Yeah,
gives the wrong impression of mathematics.
If you had,
depends what you're doing.
If you had Jim Munkers as your topology teacher, you also learned all of these things. You had to construct every single counterexample to every possible implication in your class.
Peter, is that a S of t on the right hand side of that?
Oh yeah.
And is this does the condition in 2 come from this stratification somehow?
Condition in 2.
Oh, that's nice.
Yeah. Well, this will guarantee that this is a continuous map, for example.
Oh, you're saying that if it is a continuous map, then that condition kind of has to be the case.
Yeah, I think that's something that you kind of need. Is that if you want this to be continuous, to send this point to -infinity and do what you did, just project down to t and use your stratification.
Yeah.
I think you essentially need this neighborhood around here. But
sense.
basically you should, for all intents and purposes, you should think about it in this way. I just wanted to be.
That I'm sorry, but I
don't think that's true. Yeah.
That doesn't sound right? Because you're mapping out of it. You kind of chose the weakest topology in which it's true. It's not like
Yeah, you're
So-
choosing the
kind of
smallest
choosing it.
topology with this property, right?
Yeah.
Yeah. Like what I'm saying, the push out topology is stronger. It's not weaker. So it's not like you modify it to make sure it's going to be true. You modify it to become minimal such that it's true. That's what I'm saying.
Yeah, exactly. You modify it to like in the way that you need to make sure it's true, but nothing more.
Condition 2 isn't the statement that the push out is the right thing. Condition 2 is the statement that something is open if and only if that's true.
No. What I was saying is kind of, if your counterfactual is the push out, it's not that you're saying, oh, the push out is wrong because it will make the stratification map not continuous, but rather that the push out is too, like it's more than you need. It's not less than you need. That's my point.
Yeah, this is sort of the minimal thing you need. Yeah, exactly.
2 is like the minimum that you need. It's not like
this is like the minimum that you
the coarsest topology.
Right.
Coarsest is to say initial, right? Oh, no, final. Okay.
Well, so it's the minimal thing that you need to make the stratification, this, thing that you would like to be the stratification true. But I think we should not maybe dwell too much more on this point because it's not, this is not so important in the grand scheme of things for trying to understand the ideas.
I agree that we should move on, but the compactness of T when doing this open cone construction is, I think, is an important thing to embrace. Because every now and then you use that it is the push out topology.
Yeah. So.
Oh, I see.
Yeah. That's a good point. So here's something to note. Of course, there's a closed version of this as well. Where instead of, I could have said this, if I wanted 0, from 0 to 1 or something, and then you can close up 1. So if you do the closed version of this, and then you take the realization of, say, delta n plus 1, this is this sort of closed version of the cone construction on realization of delta. So really, so really this thing that I said earlier is just a special case of this sort of example. But the point of saying this is that basically we're going to want in our sort of sufficiently nice stratified spaces, we're going to want sort of conically shaped neighborhoods like this around every point. So is everyone okay with this just construction and anything so far?
Yeah, I've learned a lot about it actually just now.
Yeah. So there's a lot more that we can say about this, and I think next week David will tell us many more things, about conical things. But for most of my talk, it's not going to be too important. It's going to be important to sort of know what the definition is, but it's not going to feature in too big of a way. So the next thing that I want to talk about is now constructible sheaves. And looks like this pen is running out a little bit. Let's see if I can.
This is the equivalent of my iPad dying. So.
Yeah, it looks like it has ink in it too, so. I don't know what's going on. 1 second. Okay, it appears to be back now. So the idea is that before we were considering locally constant sheaves, now we're considering sheaves that are locally constant along a stratification. So let S T to P, this will be a P stratified topological space. Then a sheaf F, so taking open subsets of T to spaces, is constructible with respect to the stratification F. So usually I'm just going to call this being P constructible and sort of leave the stratification implicit. If for all points in the poset, the restriction of the sheaf to the pth stratum, so this is a sheaf on this pth stratum, is locally constant. And then I'm going to write cons P of T inside of sheaves on T for the full subcategory spanned by P constructible sheaves. So the thing to note about this is that for any stratification, the locally constant sheaves are always inside of the constructible sheaves. And well, what are they? I mean, the locally constant sheaves are also equal to the sheaves that are constructible with respect to the stratification by the trivial poset. I mean, yeah. Okay. So I mean, this notation is slightly abusive because it depends on the specific math S down to P, not just the poset. But I'm just going to write it like this because it's convenient. So here's a sort of example. And of course, okay, like, spaces is not, it's not really necessary. You can do variants of this. Let me do an abelian, sheaf of abelian groups example. So T, I want to be a topological space. Z inside of T is going to be closed with open complement U. And let A be an abelian group and write A sub U in sheaves of abelian groups on U for the constant sheaf. At A. Then
this is a sheaf valued in AB, right?
Oh yeah. Sorry, AB, not in A. That doesn't make sense. So so the extension.
It could make sense.
By zero sheaf, J lower shriek of A sub U, this is constructible with respect to, let me just write the stratification as T is Z disjoint union U. the stratification defined by the decomposition of this into this closed and its open complement. But J lower shriek of the constant sheaf here is not locally constant. Well, okay, unless, well, I mean, yeah, okay. For example, like Z is the empty thing, or T, or, you know, A is equal to 0. You know, okay, sometimes it's locally constant, but usually it's not locally constant because the stalks of the sheaf, you know, on Z are all 0 because you've extended it by 0, but the stalks on U are all A. So, you know, usually it's not locally constant. Sometimes it can happen to be. So this is some example where you have some locally constant sheaf, you push it forward, and it's not locally constant, but it is constructible. And so sort of part of the point of constructible sheaves, or one point, is that push forwards of locally constant sheaves are often constructible, but not usually locally constant. So allowing for constructible sheaves allows for, you know, push forwards of these locally constant sheaves. Yeah, maybe I should say constructible with respect to some stratification.
Right. Here, can I ask, I was just thinking through this push forward construction, and I just want to make sure I have the right idea. Yeah. Is it that, so if an open contains Z, then we're asking what is the value of the left con extension, and we're like having to cover that open by opens that are contained in U, and there are just none of those. Is that the right idea to see why this is extension by 0, or equivalently why J lower shriek is the right notation?
I mean, this guy is, if you like, in the sort of Recueillement, this guy's defined to be like 0 on the Z piece. And it's defined to be this constant sheaf at U on the other piece. And then the map is the unique map.
Oh yeah, no, I was wondering why I was thinking not in terms of Recueillement, but rather in terms of like topological spaces and posets of opens and con extension over there.
Yeah. So I mean, yeah, it's because this is this, like, you know, extra adjoint to the upper star functor, the pullback functor, right? And this is always called lower shriek.
Yeah.
I don't know if that answers your question.
Well, so at the level of pre-sheaves, it's just left con extension. And I was trying to...
Yes.
Okay, great.
Yep, because the relevant over category is empty as you get up.
Okay, great. Thanks.
Okay. I'm glad your question was answered.
I had a quick question, if you don't mind.
Yeah.
So, like in exegeometry, you have sort of an object that, like, mapping out of it into, you know, the relevant version of the category of spaces gives you sort of the constructible sheaves, like for any
that's
sort
what
of.
I'm gonna ask.
Oh, you're gonna do that right now. Okay, cool. Okay.
Yeah, but well, one of the things in algebraic geometry, though, is you can work with all stratifications at once. So okay, maybe.
Yeah, I was wondering if there's like a single gadget that sort of co-classifies everything in the not algebraic geometry setting, because I was thinking about it.
Yeah, well, so the problem is that in or the special fact, I guess, about the algebra geometric setting is that the underlying space of a scheme is completely determined by all of its finite constructible stratifications. So, I mean, I guess you can, well, yeah. But I mean, yeah, like for example, you know, the underlying topological space of a manifold is not like a profinite coset. So,
I mean, mustn't there be some answer of the form like the collection of all stratifications and like, I don't know, refinements between them, and then, you know, map out of the exapath category of any one of them? And
yeah, I mean, you can
ask, is that like a filtered system or something?
Yeah, yeah. So you have to ask, yeah, is this a filtered system?
But that really sucks for like Hausdorff topological spaces.
Yeah, right. It sounds enormous.
Yeah, no, I mean it's not.
Yeah.
Well, I don't know how distracted we want to get, but I thought about that a little bit. It's bad.
Can you do something dumb like, I don't know? So for each stratification, you get like a functor from sort of like all posets or all possible stratifications into like spaces or something, or infinity categories or something. And then could you sort of like straighten that, or I guess unstraighten that into something relevant, or no?
I think the answer is no, unless you put some conditions on the kinds of stratifications you're willing to think about.
Yeah.
So for example, in the case of a scheme, what you do is you take the, you know, finite constructible stratifications where the opens that appear are all quasi-compact. Let's say that my scheme is quasi-compact and quasi-separated. And then you can do something reasonable. But you know, then you can perform the kind of construction that you're describing. But in general, it appears to be a complete nightmare. You get something that doesn't really, what's the right thing to say? You get something that doesn't compare well to your original topological space. Maybe that's what I want to say.
I'll just bootstrap on that comment that one fundamental issue with the Hausdorff class of examples is that you don't have common refinements of two stratified stratifications. The locally closed condition breaks if you try to intersect them.
So that obstructs like filteredness or co-filteredness.
Yeah, I mean, like kind of everything, I think. Yeah.
Whereas that was the thing.
Like spectral spaces, that's not a problem.
Yeah, yeah.
Thanks for saying that, David. Yeah, that's exactly the issue that I was trying to get at. Yeah.
Yeah, and so yeah, you just end up with some enormous, you know, complicated thing.
Yeah. I don't know how to fix that issue.
Yeah. Okay, are there any more things that people would like to say before I move on? Okay, I take that as a no. So, okay, so now let me try to describe what the replacement for the underlying homotopy type is. So, so this idea sort of goes back to McPherson. So the idea is that for a nice P stratified space T, we should have some sort of equivalence between P constructible sheaves on T and functors out of something called the exit path infinity category to spaces. So where exit P of T is the exit path infinity category, with, well, the first thing is that the objects, I mean, so let's go back to thinking about the underlying homotopy type or fundamental infinity groupoid of a topological space. The objects are just the points. Then in that setting, you allow any paths. But here, you know, somehow what do we want? We want to know about constructible sheaves on, or locally constant sheaves on each stratum. So those, you should allow, like, you know, any paths that stay within a stratum. And then there's some data that you need to glue these things together. And that data is encoded somehow by the poset. So we're going to allow paths that sort of exit from lower to higher strata. So I'll explain what this means. So exit paths from lower to higher strata. Okay, let me get a picture to explain what I mean by this. So okay, something that would be allowed is, you know, I start in this 0th stratum, and then I go along to the 1 stratum a bit, and then I exit to the 2 stratum. Now my pen is dying again, but it may just be because it's writing on. That's allowed. I'd also be allowed to do something like start here and do, you know, whatever I want. Or, you know, start in here and just stay in there. Let me try to get some other marker. So I'd be allowed to do stuff like that. I'd also be allowed to start here and exit like that. But what I'm not allowed to do is like start here and then go down into a lower stratum. That is not allowed. Or I'm not allowed to, like, you know, go up and then go down. That's something that's not allowed. So you're only sort of allowed to go in the direction of the poset. You're allowed to exit a stratum. You can stay in a stratum, do whatever you want. At some point you exit the stratum, and then once you exit, you're not allowed to go back to that stratum. Does that idea make sense to everyone? Okay, I guess so.
Peter, I had to step away. I'm sorry. I might have missed part of it. So right now you're describing the sort of exit paths as you'd like them to be.
Yeah.
Not as we eventually have to define them. Is that right?
Yeah, not as eventually we. Yeah. I didn't get to saying that point yet, but yes.
Okay.
So this is an idea of what this should be, but
thank you.
Okay, so there's going to be some issues with this idea. This should be 2. The 2 morphisms, well, they should be homotopies respecting stratifications, you know, and those things will be invertible, etc. So this is what you would like. And okay, so in the sort of not stratified setting, you know, it's not, you know, it's not really hard to, or well, you know, by a very modern perspective, it's not hard to make this sort of thing precise when you have the fundamental infinity groupoid. You can really make, you know, a simplicial set that has, you know, objects, the points, you know, one simplicity is the paths, you know, et cetera, et cetera. But there's going to be some issues in this setting. But okay, here's what the takeaway is supposed to be. Is that, so this exit P of T should be an infinity category with a functor to the poset P, which I'll put the N so that we don't get confused with all the various P's, with a fiber over P and P, well, in a single stratum, I was allowed to just take any path. So I should just take the underlying homotopy type of that stratum, the fundamental infinity groupoid. Yeah, so in particular, this means that the functor here is conservative. So yeah, what it means for a functor from an arbitrary infinity category to a poset to be conservative is exactly that the fibers over every point are infinity groupoids, because the only equivalences in a poset are the identities.
So conservative right now means that everything that goes to an equivalence already is an equivalence. Is that the idea?
Yeah, exactly. Conservative means if f of the morphism is an equivalence, then it wasn't already an equivalence.
Right.
Yeah. So okay. So okay, this is the idea, but the construction is gonna be a little bit more difficult to, than in the sort of usual setting, but nonetheless, we have a sort of candidate construction for this. Let me explain how this works. So here's a construction. I think this goes back, I mean, maybe even further, but as far as I know, to Andre Enriquez and Jacob Lurie. So P will be a poset. So the sort of observation is that the functor that I'm going to do realization sub P is what I'm going to call it, from simplicial sets over the nerve of P to topological spaces over P in this Alexandrov topology, that it's going to send K over the nerve of P to, well, I can take the realization of K that maps to the realization of the nerve of P, and then I have this canonical stratification that I defined earlier, and I just post-compose with that. That was the stratification that I said I define them for all delta n's, and then I use the fact that every poset is a colimit over its subdivision. So that this is a left adjoint with a right adjoint, well, what it has to be. So so we call the right adjoint sing sub P. So this goes from P stratified topological spaces to simplicial sets over the nerve of P. That, what does it do? So if you have your P stratified topological space like this, well, what you can do is you can take the singular simplicial set of this and the singular simplicial set of this here. Now, there's a map from the nerve of P to here that this is adjoint to this canonical stratification, and you can perform this one categorical pullback. So actually, this is a monomorphism, so this is a monomorphism. So it's some sub-simplicial set of this guy. Yeah, so here's a node if you trace through the definitions, if you take this sing P of T and you cross it over with the nerve of P with a point little p, this is just isomorphic to the simplicial set sing of the pth stratum. So based off of this idea, this is kind of looking good for as a candidate for this exit path thing. You know, it's some simplicial set over the nerve of P. You know, over every point, I get the, you know, underlying homotopy type of that stratum. That's looking pretty good. So, so sing P of T is the candidate for this exit thing. Also, I mean, if you trace out what the definition is, the one simplices in here are some version of exit paths. Though what exactly they mean is basically you have to exit the stratum immediately, kind of. But here's the big warning. Dun dun dun. So this is the warning that for various points of my life has been the bane of my existence, is that unlike with sing, so if I take sing of just any topological space, I get a Kahn complex. Sing P of T generally isn't a quasi-category. This is kind of unfortunate in certain ways, but yeah. So
I just want to
illustrate that for us.
Oh, hang on.
Yes,
but the fibers,
I'm going to do that.
But those fibers are Kahn, right?
Yeah, those fibers are Kahn because they're saying of
just not assembled the right way. Is that?
Yeah, not necessarily. And I mean, the reason basically is that somehow exit paths can like kind of fail to compose. So let me try to illustrate this and try to use the same colors I used before. So what was my next color? Oh, orange. So this will be 0, 1. And so I want to think about this horn, the sort of geometric realization of the horn inside of this stratified 2 simplex. So let's see if I can do this in some reasonable way. I want to think about this horn inside of this stratified 2 simplex. Mm-hmm. And the point is that, okay, you have to, you know, go through some definitions, but if you look at one of the horn filling conditions that you would need for this to be a quasi-category, what you need is to have, you know, sort of a special case of one of the horn filling conditions is you need a retraction of this guy onto this guy that respects the stratifications. But I mean, there is no such retraction that respects the stratifications, because like, you know, you have to send all of the orange piece here to orange here, but you can't make a continuous map that sends this red point to the red point and then sends, you know, a point very close to it all the way over here, you know, somewhere in the orange.
So to unpack that a little bit, I mean, so if you had, you could imagine having an exit path that goes from 0 out all the way to that endpoint, to that vertex that you wrote down, because that's still green, right?
Yeah.
And then you can write an exit path from that endpoint there somewhere into the second stratum, wherever you want to go, really.
Such as the topological example, which is that stratified topological space that we're staring at.
Yeah.
Yeah.
But then the point is that doesn't have a composite anymore. Because of this weird condition that I have to exit the stratum immediately in order to qualify as an exit path. with this definition that you've given.
Yeah.
So implicit here, is there, I feel like these standardly stratified topological simplices are part, is that what's co-representing sing P of T, or that construction? Or I'm trying to see where it is in this restriction to the adjoint to can. In that, somewhere in that restriction is the demand that paths exit immediately. Is that right?
Yeah,
because like
exactly.
those are the ones that those pick up. Okay.
Yeah, exactly.
But,
so like if you look at the one simplices.
Just to verify, right? It's not only that you exit immediately. It's that once you exit, you only, if you're a path, you only see at most 2 stratas, right?
Yes. Yeah.
Yeah.
You
That's
never
also
see
true.
3 strata. It's not like you.
That's right.
You can exit, but also then you never exit again.
Yeah. What I mean is that you exit into the next stratum and you stay there. Yeah.
Right.
Yeah.
Right. And then for 2-dimensional or for composites, it has to be shaped like the thing Peter was showing us.
Yeah. So it has to be shaped like Yeah. So I mean, this is a bit unfortunate in certain ways, though not all is lost. Not all is lost. So, and that's what I'm going to try to explain in the rest of the talk. Not all is lost.
That's a good sentiment for these times.
Yeah. So, okay.
So do we have an exit path strategy?
Oh, that was good. So, that was good. Okay. So here, let me, not all is lost. We're going to talk about conical stratifications. So, I mean, somehow the problem here, part of the problem here is that you don't, right, you can't push this this stratified 2 simplex onto this thing. But if you're you sort of locally look like you have all these, stratified simplices that you can put, that exist locally, then you're actually okay. So P stratification T to P is conical if for every point, so T in T, but this will be in some particular stratum T sub P, there exists an open embedding V crossed with a cone on T prime. That's going to be an open embedding to T. So let's call this stratification S. So it's going to be an embedding respecting the stratification. So this T prime, this guy here is going to be P greater than P stratified space. So if I take the cone on it, it's going to have a stratification down to P, including the element P. Right. So this is just by, so you project onto the place that you have the stratification, and you want this to respect the stratifications. So it looks like this. And okay, well, you want this guy to be an open neighborhood of your point. So I guess T is in the image of J. Okay, so so this is just a definition, but the point is that in the setting of this definition, that this Sing P construction is actually going to produce a quasi-category. So maybe let me just mention quickly that in this sort of work of Goreski-McPherson on intersection homology, they always talk about these topologically stratified spaces. And these implicitly have this sort of cone condition. But your neighborhoods always have to look like a copy of a Euclidean space crossed a cone on some compact topologically stratified space of over a smaller poset. And a particular example of those, though, there's this theorem of Tom and Mather that shows that all Whitney stratified spaces are topologically stratified. So in particular, they admit these conical neighborhoods around every point. Mm-hmm. So yeah. So here's the theorem that is a pretty cool result. Very difficult to prove. Of Lurie, so this is in higher algebra 8.6.4. So the theorem is that if T to P is conically stratified, then this Sing P of T is a quasi-category. So it really, it really kind of does the job of what we wanted this exit path thing to do. So in this case, we'll write exit P of T for this guy, Sing P of T, regarding it as an infinity. Yeah, this is, I mean, if you look at this, the proof of this is like 5 pages long, and it like, essentially it, does all these reductions and reductions and reductions to essentially some sort of simplex type case, and then it writes down a ton of explicit homotopies, and it's kind of complicated. But part of the point is that, yeah, someone should correct me if this is not true, but I think essentially this is the only like reasonable geometric condition that we have to guarantee that this Sing P construction spits out a quasi-category.
I wonder if it's a necessary condition.
No, I mean, it's not necessary. You can construct examples that aren't conically stratified, but still give you quasi-categories.
Thanks. Can we see the failure of the above one to be conically stratified?
Yeah. So, yeah. So let me bring this up here. So yeah, what would we need? So let me try to remember the best way of seeing this. So I think, yeah, I think part of the problem maybe is like at this point. Yeah, what would you need? So, right. So I'd need to have, like at this point, here, this point labeled 1, I would need to have an open embedding of a cone on this, on something stratified over a bigger thing, crossed something else into here.
I don't think that will be the issue, because that's just
maybe
really
that's not
restricting to the one simplex. I think the issue is the deepest stratum, 0.
Oh, maybe it's the yeah. So yeah, so here.
Although maybe the middle points of the green are also a problem, just not the end point.
A cone.
I mean, I'd like to understand this example at least.
Yeah.
I think it is the point 1. The issue
yeah, I think it is the point 1.
If you want a neighborhood which looks like a product, then then you can't have it like you can do it, but then it can't respect the stratification because it has to go over. It has to spread on both the two and the one. That's the green and the orange. That's the issue, right?
Yeah, because like, I mean,
sorry, what would the guess be of like T prime? And so T prime would be a point, right?
Yeah, and then, okay, what's the problem?
And V would be a point.
Yeah, and then what's the problem? For example, that wouldn't be open, right? Because you'd have like this like open piece, half open interval, and then this guy, you know, is the point like minus infinity in that cone construction. But in this big space,
the image of an open is open. That's the definition, and that fails here. Okay.
Yeah, that fails. Yeah, so but nonetheless, there's all these examples that come from like intersection homology and stuff that do satisfy this.
So Peter, can I just ask? I mean, so if we go back to that Horn example, the lambda 2-1. So what you're saying is that if I were willing to just fatten that up just a tiniest bit, and have like a little, you know, approximation as sort of 1 over x to the n type approximation to.
Yeah, if you were willing to like, you know, add in like literally as small as you wanted, thing like this.
Where all of that stuff, all of that new material, all has to be in the second stratum.
Yeah.
Then I'd be good. That's what you're saying.
Yeah, because like that guy is stratified homotopy equivalent to the, you know, the actual 2 simplex with that stratification.
Okay, I see.
I mean, that's even homeomorphic, right?
Yeah, I mean, it's even homeomorphic.
Yeah, that's right.
Yeah.
Yeah, right. Good point.
But epsilon is so small.
Yeah, it's even homeomorphic. Yeah.
All right. Okay.
So,
yeah. Fine. Y'all can make fun.
Yeah. But
I don't even see the difference. I don't know what you guys are talking about.
He's a true topologist.
That's how you know. Yeah, Tomer is a true.
Pour your coffee into a donut.
Yeah. So okay. So what now we finally, after this, you know, hour and 45 minutes or something, have enough to actually state the theorem in this set. So here's the theorem. So in a weaker form, this was proven by David Truman. And in the form I'm stating it, it's going to be due to Lurie, a 0.9.3. So there's going to be some points at topological conditions. So let T be a paracompact topological space, which is locally of singular shape. Okay, this just means that the monodromy thing that Clark talked about in the first talk, you know, your space is nice enough for that equivalence to be true. So P will be a poset satisfying the ascending chain condition and S from T to P a conical stratification. So then there's an equivalence of infinity categories. So, okay, there's a reason why I did this thing at the very beginning where I described this functor that way. because, so I mean, on the one hand, you're going to have constructible sheaves, but I'm going to write it sort of in the opposite direction of how you might usually think about it. So functors from the exit path thing, that's just saying P. I'm just going to call it this because I like the name better. And it's going to be an equivalence between P constructible sheaves and functors out of this exit path guy. And that's a subcategory of sheaves on T. And you know, how is this functor going to work? Well, yeah, so by straightening, unstraightening, again, this is equivalent to left vibrations over this exit path thing. And I'll define the functor that way. So this will be an equivalence. And it's going to send my y over my exit path thing. Is going to go to the same exact formula as before, except I replaced fundamental infinity groupoid by the exit path thing. So U goes to functors over exit P of T from exit P of U to Y. Now, it turns out, maybe a fun exercise to think about why this is true, just in the definitions, that this is actually an infinite groupoid. Everything's invertible. Okay.
So is exit PU over exit PT always a left vibration in particular?
Exit PU over exit PT. Yeah, in this, yeah,
well,
is it going to be a left vibration?
No, I think not at the point set level, but I mean, infinity categorically it is. Every space down
to... Yeah, no, I mean in the invariant sense.
Yeah,
in the invariant sense, yeah. Yeah. So am I right that the conditions that make sing P into exit P those are local, which is why you're entitled to write exit P of U?
Yeah, that's why I'm entitled to write exit P of U. So
awesome.
Yeah, it's a local condition because, you know, it's saying like, you know, around every point you have this neighborhood, right? And U is an open. So you know, that's allowed. Maybe let me say a few other things about, yeah, like where does, maybe let me do this in red. Like this paracompactness and ascending chain condition. So these come in part because here, every object is the limit of its Postnikov tower. And okay, so in general, in sheaves of spaces on a topological space, in general, it's not true that every object is the limit of its Postnikov tower. So, I mean, you couldn't...
The example is some Hilbert cube something?
Yeah, so, yeah, for example, yeah, sheaves on the Hilbert cube. So that's a countable product of the unit interval with itself. That's not, I mean, it's not hypercomplete if you know what this means, but in particular, not everything is the limit of its Postnikov tower. So you need some conditions to guarantee that the constructible sheaves will always be the limits of their Postnikov tower. And essentially that's part of where this paracompactness and ascending chain condition comes in, is to guarantee that the constructible sheaves will be the limit of their Postnikov tower. Okay. And so, so we call this.
Could I ask, could one say then that the thing on the left is the right object in the absence of those conditions, or is that not the way I should think?
That's the way I think.
If
that's the way.
If breaks down, then we discard the thing on the right somehow.
Yeah, well, I mean,
somehow what you're saying.
Well, yeah, I mean, I guess.
Can we not just drop the ascending chain condition and then put hypercomplete on the right side?
Well, I'm not sure you can just do that, actually.
Okay. Okay.
So, I mean, this is a sort of heuristic, but I'm not 100% sure that you can just do that, actually.
I don't think you can. What if you do something more aggressive? What if you take sheaf of n truncated spaces? Can you then remove power compact and ascending chain conditions?
You can remove, in that case, paracompactness, but not the ascending chain condition, I think.
Yeah, probably.
I think that's correct also.
Yeah.
Like
that sounds right.
Yeah.
So like this goes back to this fact that the being sober as a topological space, if you're a poset, is the same as that ascending chain condition.
Yeah.
So you're trying to argue. I hope I haven't said this wrong. You're trying to argue that the functors from your poset are the same things as sheaves on your poset with the Alexandrov topology. And I think you only know that in the case where the thing is actually an Etherion or satisfies the ascending chain condition.
Arcadian.
Right.
Wait, is that Arcadian now?
I think so.
Well,
it depends on the. So there's an example that I find instructive of so the Ron space of a manifold does not satisfy, it's paracompact, but does not satisfy the ascending chain condition.
Right.
And Constructible sheet, you can model with a bit more structure, you can model EN algebras as constructible co-sheaves on the Ron space of Rn. And hypercompleteness amounts to that, to the associative EN algebra being pronilpotent, which is a genuine condition. So that's an example to keep in mind, that there's this algebraic condition that I think prevents a statement like this from being true without if you were to try to drop the ascending chain condition.
While I'm unmuted, could I ask, is exit paths of U a left fibrant over exit paths of T? Just double checking.
Well, it's co-fibrant in the model structure, if that's what you want.
Co-fibrant, but is it fibrant? Because we've written morphism in left fibrations.
There's no way. You can find it's not an isofibration.
Can't be, right?
Oh, not an iso, but left. Oh, not an iso. Okay. And is U, by the way, is U automatically conically stratified if T is?
Yeah, because it's a local condition.
Oh, it's okay. So that part's good. It is actually a quasi-category.
Yeah, and so I mean to also mention, I mean how this works is, I mean, really. Jacob writes this down, in a model categorical way. Mm-hmm. This factor, right. And so this is done in detail in higher algebra.
But it is co-fibrant.
It is co-fibrant. There's a model structure on all simplicial sets over that models the infinity category of left fibrations, and once again, everybody's co-fibrant.
But this formula is not literally in, unless you take. Unless...
No, you can do it at the point set level, or at the simplicial set level, yeah.
I know,
you can do it.
What I'm saying is that the formula on the right isn't actually in the thing on the left, that's all. It's just a small linguistic remark.
Yeah, he's pointing out that he wants to form that formula where you're looking only at left fibrations.
Yeah.
And that's not quite right.
That's not quite right, but yeah,
so I should
but that's okay. You don't need to
vibrations as being in fact, some simplicial localization of all morphisms with respect to the appropriate covariant equivalence.
Great. Totally.
100%. Yeah.
Okay, thank you. Just checking. Okay.
No, I appreciate your connecting it to the model categories. That's nice.
Yeah.
Yeah, so
can I just
okay.
Excuse me?
Yeah.
So if I take one of these Noetherian posets, is it necessarily paracompact, so the identity is there?
Is an Etherian poset necessarily paracompact? Oh shit, Jay, come on.
Yeah.
Let's see. Let me just think. Is this obvious to someone else? Because if it is, please chime in now. Don't make me suffer.
Isn't it quasi-compact if it's Etherian?
I don't think so.
Okay.
Well, it seems likely, just from the definition. I mean, paracompact has to do with refining open covers, and the ascending chain condition is about upwards stuff, which is where the openness lives in the poset.
Yeah.
Which is not an answer, but it makes it seem plausible.
Yeah.
Yeah, and I mean, I think, right, certainly it's going to be, like, if you take the realization of the nerve of P, it's always going to be in here. And that, I mean, I should mention that if you take the exit path category of the realization of the nerve of P, it's equivalent to the nerve of P.
And it's definitely also always paracompact. Sorry, I don't want to distract Peter. Sorry, Jay. Yeah, let's. It's true. I can explain later. Yeah.
Yeah. So I mean, okay. Since we're already at 5, 5 o'clock my time, whatever o'clock everyone else's time. Maybe let me delay. Let me delay 0.6 for next time. I think I'll try to say a little bit about this next time. And I don't think it'll take too long. And then I think also next time David's going to tell us about conically stratified things, or conically smooth stratified things, which will connect to 0.6. But maybe let me just very quickly give one example. So.
Yeah.
Okay, so here's a kind of cute example that connects this stuff to equivariant homotopy theory. So I'm going to do this in a specific case and then say a little bit about generalizing it slightly. So, so recall that the underlying homotopy type of the topological space RP infinity, this is a classifying space for the cyclic group of order 2. And so there's a computation that you can do. So as long as everything's sufficiently nice so that this is defined. So if I have a nice stratified topological space, then if I take the exit path category of the cone on that stratified topological space, stratified over this poset with an additional minus infinity, that this is equivalent to the exit path category with a new initial object adjoined. Mm-hmm. Okay, so in particular, if I take the exit path category over the poset 0 is less than 1 of the cone on the, just completely unstratified topological space RP infinity. Well, this is, I take the underlying homotopy type of RP infinity and I adjoin an initial object. So this is BC2 and I adjoin an initial object. And if you've thought about this before, it's probably clear that this is the orbit category of C2 off. So what you deduce is that if you look at constructible sheaves with respect to the stratification on the cone on RP infinity, you get pre-sheaves on the orbit category. So this is also known as C2 spaces. And okay, of course, this is, this isn't so specific to this. If you wanted to work with CP here, you could replace this with some geometric model for BCP. So for example, one of these like lens spaces. I mean, for more complicated groups, it's not, not as simple as this, but I think there's a nice sort of example to connect these constructible sheaves to other things. So, I mean, somehow these are very related to equivariant homotopy theory.
I love that example.
Yeah, I really like this example. It's really nice. Yeah, but let me delay the stuff about the homotopy theory of stratified spaces to like the first like 30 minutes of next time, maybe. Or so, I'll try not to talk for too long.
Well, so pursuant to that, okay, so first of all, before we talk about organizational things, can we all thank Peter, please?